Hello and welcome. Today we're going to be learning about physics. And before we get started, I just want to say nobody is bad at math. Just like in Ratatouille, the book Anyone Can Cook, I'm going to change this book to Anyone Can Do Physics. So I want you to remember that. It's really confusing at first and it can feel overwhelming because you're learning an entirely new language. So there's lots of symbols, equations, and vocabulary that we don't know yet. But just like learning anything else, we just practice it and it's really fun as things start coming together. When I was in high school and college, I really thought I was just, oh, I'm bad at math. And I kind of avoided it. I had this irrational fear of, oh, I'm just not a math person. But guess what? I am a math person. Everyone's a math person. I just didn't know what I needed to do. I didn't have the right information. But anyone can do physics, anyone can do math, and that's what we're going to do today. So before we begin, I want you to grab your notebook, your iPad, whatever you're using to take notes on it. I want you to pause the video here and write down these formulas. These are what we're going to use today. All right, if you wrote these down and you're wondering what they are, we will find that out. We have our little cheat sheet here, so don't panic when you see these. Every equation here is just telling a story, and we're going to learn these characters as we go. So when we have our V1, we see that a lot. V1, that's going to be our initial velocity. And then VF is going to be final. So 1 initial beginning, F final, the end. A is our acceleration. D can be distance or displacement, depending on the question. Our T is time, our M is mass. So the first thing when we're reading a physics problem is we're going to identify what information we have. So we're going to look and we're going to say, okay, what do I know? What am I trying to find? And one of these equations is going to connect those things for me. Also, we're going to need to know our units. So let's put this on our cheat sheet as well. So this will come up here. So 1 kilometer is going to equal 1,000 meters, and 1 hour is going to be 3,600 seconds. So 60 minutes an hour, 3,600 seconds an hour. So we always got to check our units too when we're doing a physics problem, because they're only going to work if our units match. So if our speed is meters per second, the distance has to be in meters as well. Okay, I think we're ready for our first example problem. Our question is, a goose flies 845 kilometers at 28 meters per second. How long does it take? Okay, before we calculate anything, let's take a look at our cheat sheet. And what equation are we going to use? What are we looking for? You might be saying, Miss Amanda, this is not the equation you gave us. Time equals distance over velocity. This is velocity equals distance over time. What's going on? Well, we have to think of these equations kind of like a triangle. So they can kind of be interchanged. So we'll put our distance here, our V, and our T. So we'll have it in a little triangle like this. So if we want velocity, the velocity is what we want. So we'll put our equal sign here. But if we want distance, our distance sign will have an equal sign right here. We'll multiply those. And if we want time, we'll put our equal sign at time and divide those. So it is a mix and match type of equation. So that's how we got this. Time equals distance over velocity. A goose flies 845 kilometers at 28 meters per second. What's something else that we notice? Ooh, our units. Our units do not match. So this 845 kilometers needs to become meters. So let's look at our cheat sheet. How do we do that? We multiply by 1,000. So this 845 becomes 845,000 meters. Okay. Now we have our units matching. So we have our equation, time equals distance over velocity. So we'll go time equals, we have our new and improved distance over 228. And then we solve. So we'll divide this. The good thing about physics to physics, we use our calculators. So pop that in your calculator. All right, we have 30,179 seconds. Remember up here on our cheat sheet, 1 hour is 3,600 seconds. So let's divide by our 3,600 and we should get 8.38 hours. And that is our answer. So what did we do? We found the equation, step 1. We made sure our units matched. Step 2, and then we just plugged in our numbers. Step 3, and then step 4, we made sure our units were the same again. So a lot of this, basically all physics is knowing what equation to use, making sure the units match, and then making sure the units match again. Easy breezy, right? Let's try some more. Okay, we're going to try one more example of this before moving on. Remember, we don't need to memorize the formulas. We just need to recognize what the question is asking us to find. So here's our next question. A runner travels 12 kilometers at an average speed of 4 meters per second. How long does the runner travel? All right, so let's first identify which information we are given. We have our distance, 12 kilometers. We have our speed, 4 meters per second. What are we looking for again? Time. So what equation are we going to use for this? Time equals, there you go. Step 1, find the equation. All right. Remember, before we plug in our numbers, we need to look at our units. They always need to match. So right here we have kilometers, and right here we have meters per second. So our distance needs to be in meters. So remember, to get this kilometer into meters, we need to multiply it by 1,000. So now we have a new distance of 12,000 meters and 4.0 meters per second. So what I did here, we just step 2, convert. For step 3, all we did was we took this formula and plugged our numbers in. So now we just solve and we should get 3,000 what? 3,000 seconds. And we can actually leave this one in seconds because that's the unit from our formula. But if it asks how many minutes or it asks us to convert it, how we would convert this would just be divide by 60, and that would get us 50 minutes. Both are correct. It really depends on what the formula is asking. All right, so remember, notice this pattern here. We look at what the information we have in the problem and what we're looking for, and then we find our formula. Then we make sure our units match, and then we solve it. Okay, I'm going to give you a challenge question for you to solve on your own. A cyclist travels 90 kilometers in 3 hours. What is the cyclist's average speed? So feel free to pause the video if you need. I'm going to leave these up here so you can see what steps we did. We are looking for the speed. So let's look up here. Velocity equals distance over time. So we're going to be doing velocity equals distance over time. And then let's plug in our numbers. 90 kilometers goes for distance and time, 3 hours. So we just divide 90 by 3. and that gets us 30 kilometers per hour. So same general idea, but we didn't have to do our converting. Okay, let's move on. Now that we understand speed, distance, and time, the next thing we need to talk about is one of the biggest places students get confused in physics, distance versus displacement. They both have RD, but they're going to mean different things. So distance is going to be our total path traveled, and displacement is going to be a change in position from start to finish. Distance is going to be the entire journey. Doesn't matter what direction you're going. You just add up how far you've traveled. Displacement cares about where you end compared to where you started. So it's going to be the shortest straight line path between where you ended compared to where you started. All right, let's do an example problem for this one. A postal worker walks 161 meters due east from his truck. He then turns around and walks 194 meters due west. What is the worker's displacement relative to his truck? Okay, so remember our steps. What is the question asking for? It says displacement right here. So we know we are not going to be adding two distances together. So let's draw this out. Here's our truck. And this truck went 100. I'll make us a little compass here. Our truck went 161 meters east. It turned around and went 194 meters west. So the worker went 161 meters away from the truck and then came back 194 meters toward the truck. Since he walked further west than east, he ended up 33 meters west of the truck. So he's over here. We got the 33. We just subtracted this. We subtracted this from this, and that gave us 33. So our little guy, he's right here, 33 meters west of the truck. Let's compare that to distance. If this same question asked for the total distance this person traveled, what would we do? We would just add it. We would just add this 161 to 194. That's all the total distance that he walked. So that would be the difference between distance and displacement. So distance, a good memory trick is how much ground did he cover walking here? Let's add it up and we're going to find out how much ground he covered. Displacement, where did he end compared to where he started at the truck and in his path here? So this is where he ended up. This is where he started. The displacement is that. All right, we're going to now talk about acceleration. So this is a big concept in physics because a lot of us think, oh, acceleration, that means something's moving fast like a car. That's not all it means. So acceleration means the velocity is changing. So acceleration is a change in velocity and time. So we go look up here to our cheat sheet. Let's put down our acceleration formula. Acceleration equals triangle V over T. What does this little triangle mean? The triangle just means change. And acceleration is going to tell us how much the velocity changes every second. So if acceleration is 5 meters per second, that means that the speed increases by 5 meters per second every second. So acceleration is a car speeding up. Yes, that's acceleration. A car slowing down, also acceleration. A car turning, also acceleration. So velocity has two parts, speed and direction. So acceleration happens anytime speed changes or direction changes. Let's do an example problem together. A car starts from rest and accelerates at a constant rate of 5 meters per second. How fast is the car moving after 3 seconds? So, what equation are we going to use for this one? What do we know? We know that the car starts from rest, so our initial velocity is going to be zero because it's starting at rest. We know acceleration, it tells us that in the question. And we know the time, 3 seconds. So what we need is our final velocity. Let's look up here. The final velocity. Okay, we're going to grab this from our cheat sheet here and we're going to move it down with us so we can look at it. What do we know? We have our initial velocity starts at rest. That's a hint that the initial velocity will be zero if it says starts at rest. Acceleration, we have that too. Accelerates at 5 meters per second. Time, we also have right here is our time. We're looking for how fast the car is moving after 3 seconds. So that would be our VF, remember, which is our final velocity, F for final. Because we're going to find our velocity, we're going to use our velocity equation. VF, final velocity, equals V1, initial velocity, plus AT, acceleration, and time. So let's just plug in our numbers here. We just bring everything down here with our numbers that we do have, and now our equation should look like this. Let's solve it. 5 times 3 gets us 15. So our answer would be 15 meters per second. This means that the car's speed increases by 5 meters per second every second. So at 0 seconds, it'd be going 0. At 1 second, we have 5 meters per second. At 2 seconds, it'd be at 10 meters per second. And at 3 seconds, it'd be 15 meters per second. Okay, now that we've covered acceleration, we can move on to forces. What is a force? A force is a push or pull that can change an object's motion. So the acceleration is going to happen when the velocity changes, but the force is what causes that acceleration. Newton's second law is force equals mass times acceleration. So this equation tells us 3 things. Force depends on mass and acceleration. The more force you apply, the more something accelerates. So think about our ball. If we kick it really hard, it's going to go way farther than if we just gave it a gentle tap. And the more mass something has, the harder it is to accelerate. So think about this soccer ball we're kicking on the ground. What if I turned it into a bowling ball and gave it more mass? It's going to be a lot harder to kick a bowling ball and make it accelerate as fast or go as far as a soccer ball. Another way to think about it is when you're at the grocery store. So if I'm pushing an empty shopping cart, it accelerates pretty easy. I can push it really fast, it accelerates easy. But if it's a shopping cart full of groceries and water bottles and it's really heavy, it's not going to be as easy to push around the store. I have to use a lot more force to push it and get the same amount of acceleration because since we added all those water bottles in there, the mass is bigger. Let's do an example problem for force. A 975 kilogram car accelerates from rest to 26.7 meters per second in a distance of 120 meters. What is the magnitude of the average net force acting on the car? So before we solve, let's ask ourselves these questions. What are we looking for? Okay, we're looking for the force. What formula do we know for force? Well, would you look at that? We have it right here. So we have our formula. But, uh-oh, we don't have acceleration. So before we can use this force equals mass times acceleration, we need to find the acceleration. So this happens quite a bit in physics when we're doing problems. Sometimes the equation that we need is not going to be the first equation we use. So although we need to use this equation eventually, we need to find the A in this equation to be able to solve for it. So what do we know so far? We have mass, we have initial velocity, which is going to be 0 because it's starting from rest. So always look, if it says starts from rest, just like in our other problem, start from rest, it's going to be 0 for initial velocity. And we also have our final velocity of 26.7 meters per second. We also have the distance. And what do we need to find is A. A is our mystery. So we need to find an equation that's going to connect velocity, acceleration, and distance. Since we do not have time, we don't know the time in this, so we can't use one that has time. So what we're going to need to use is this. So we have velocity final equals initial velocity plus 2AD. What's A? Acceleration. What's D? Distance. So we have most of these numbers. Let's plug those in. We have our final velocity. Don't forget to put the squared symbol. Let's bring down our equal sign, and then let's look. Oh, we do have our initial velocity. Let's bring that down. It's going to be 0 because it starts at rest. Always 0 if it starts at rest. Bring down our squared symbol. Plus, we'll just bring this 2 right down. A, ooh, A is what we're looking for, so we don't have it. So let's put in our A. And D, we do have our D. Let's look over here, 120 meters. Awesome. Now all we do is solve. Put it in your calculator, remember. We double it, and we keep our A that we're looking for. Then we divide this. Okay, so we got this from here. We got this from here. And now we divide these two numbers. So 7, 12, that one divided by that. Then we divide these two, and we should be getting 2.97 meters per second. Oh, but we're not done yet. We found our acceleration, but the question is asking for force. So we did step 1. Let's fill this in. We have acceleration now. Now we can go back to our initial force equation. So force equals mass times acceleration. Let's plug in these numbers. We have our mass and we have our acceleration. Type those in and we should get 2,895 N. What's N? N is newtons. And let's put this into scientific methods so it's easier to read. Also, speaking of easier to read, I'm going to do a darker color here. Okay, I don't know how to get this square off, but okay, we multiplied mass times acceleration, and we got, after solving that, our answer was 2,895 newtons. And that's a big number. So we're going to want to put this into our scientific method. So how we do that is we start at the end of the number right here, and we move 1, 2, 3 spots over and put a big old decimal point right here. And we moved 1, 2, 3 spots over. So when we rewrite this, we're going to rewrite it to point. Let's round this 895 up. We're going to round that up to 9. 2.9 times 10 to the third power newtons. Why is it 10 to the third power? Because we moved 1, 2, 3 times to get the decimal up. And this is our final answer. That is the force acting on the car. Now we're going to take everything we just learned, velocity, acceleration, and forces, and we're going to apply it to our next topic, which is projectile motion. So that's going to be when something is launched into the air and follows a curved path. So, hi, this is you. And you're going to throw a baseball. Ooh, and imagine when you throw the baseball, it starts, it goes up, and it goes down on a curved path. So the projectile motion is going in two directions. It's going up, so see it went up, and it's going this way. So the horizontal is what we would call our X, and then the vertical motion would be what we call our Y. So the biggest thing to remember in projectile motion is that these two directions are going to behave differently. So the horizontal motion is usually constant because we ignore the air resistance in these problems. The vertical motion is going to be affected by gravity. And remember, gravity always, always, always is going to equal 9.8 meters per second. We should add that to our cheat sheet notes. Gravity is always going to be 9.8 meters per second. So this is why projectile motion problems can start to seem confusing. So you are going to be solving two separate problems happening at the same time because you're going to be looking for the X and for the Y. The ball is moving forward because of a horizontal velocity, but then it falls because the gravity is pulling it downward. When we see projectile motion, we'll get problems like this. So let's ask our questions we always ask. So what are we trying to find in this question? Is the distance. How far does it travel? What direction is distance? That would be horizontal. So we know we'll initially need to find that horizontal velocity. But projectile motion is going to require us to break the velocity into two parts, the X and the Y. So that is something that we will cover in our next video. Yay! Let's recap what we learned today in our physics overview. So we learned about our problem checklist. We're going to say, what information do I know? What am I solving for? What equation connects these things? Do my units match? And does my answer make sense? It's about recognizing patterns in these questions that were asked. So when I see speed, distance, and time, we got to think about the relationship between those three. When you see acceleration, think about the changes in the velocity. When you see force, we think F equals ma, Newton's second law. And then when we see constant velocity, we remember that if there's no acceleration, there's going to be no net force. Anyone can do physics. Nobody is bad at physics or math. These are all skills that will improve with practice. And the more you expose yourself to it and the more you think about it, the pieces, they will start connecting and you'll see how everything relates to one another. And it becomes really interesting and really exciting because once you understand physics, you start looking at the world in a different way and thinking about how the world works. And it's really fun. So in the next video, we're going to dive deeper into projectile motion, vectors, and then how to break these problems into simple steps. So thank you so much for learning with me today, and I will see you in the next one.